So today we're thrilled to have Cheng visiting us from MIT, and Xiang is an incoming faculty into the Duke Electrical Engineering Department. He is currently a TILOS postdoc. So welcome first to the TILOS Seminar. He is currently a TILOS postdoc working with Suresh at MIT, and previously he was a PhD student working with Mike Jordan at Berkeley. But without further ado, maybe let Xiang take it over.
Okay, thank you, Yang. And thanks everyone for coming. So I'm Xiang, and today I'll be telling you about the ability of transformers to implement interesting learning algorithms, partly motivated by this phenomenon known as in-context learning. So without further ado, let me just get started. Okay. So I guess over the past year or two, a question that is at the back of many of our minds is why do large language models work so well? So on the left, I show a sketch of the GPT's architecture, and when we zoom in, we see that it is essentially stacks of blocks of the transformer neural network. And if we zoom in on the transformer some more, we see that it is essentially stacking both sequentially and in parallel the attention module. And so the transformer, and specifically the attention module, lies at the heart of modern large language models, a fact alluded to even in the title of that famous paper, which originally proposed the transformer architecture. So in this talk, we'll consider a simplified transformer model for the most part, which is obtained by sequentially stacking attention layers. And if you're already familiar with transformers, this is specifically single-headed attention. And the central message of the talk is that the transformer naturally learns to implement a gradient descent algorithm in the spiral path. And specifically, each layer of the transformer implements exactly one step of some kind of gradient descent. And one of the motivations for this investigation is a remarkable phenomenon known as in-context learning. An important task that large language models need to perform is that of next word prediction. So here's an example. In-context learning refers to the ability of the large language model to answer the query based on the examples that you provided that gives context. For instance, when I ask what are grapes and I give two demonstrations, apples are red and bananas are yellow, the model correctly infers that I'm asking about the color and answers that grapes are purple. Based on the context, the same question can have different answers. So if instead I give two examples that lemons are sour and cranberries are bitter, then the language model to the same question of what are grapes instead answers that grapes are sweet. So this phenomenon is surprising because the language model learns from the demonstrations, but does not need to make any updates to its parameters. So in other words, the learning happens entirely in the forward pass. And the phenomenon of in-context learning was first observed and reported in an influential paper by Brown and collaborators. And because contextual information is so important in human language, some people have even gone as far as to hypothesize that the in-context learning capability is why large language models work so well in practice. But in any case, how large language models achieve in-context learning is a very important question. And as we can see, the answer to this question has to do with a natural affinity for transformers to implement learning algorithms. So before going into specific papers, let me recap on a brief history of a line of work which led to the papers I'm going to talk about. So at the very top of the slide is the paper by Brown, Mann, Ryder, and Subian, which we saw on the last slide. And they basically observed in a qualitative sense that these large language models appear to be able to infer information from the context. And so following up on this paper, a paper by Garg, Tsipras, Liang, and Valiant in 2022, they focused on a subset of the problems, which is whether transformers can be trained to learn relatively simple functions in context. Relatively simple as in things like linear functions or two-layer networks or decision trees. So the important contribution here is that they formalized quantitatively the problem of in-context learning, and they showed which I guess I illustrate on the slide, right? So instead of the question and answer being words, you're given like x, y pairs, and x is a feature vector, y is a label, and you want to predict y as a function of x. So in this particular example, y is a linear function of x. The star is the hidden parameter that the language model needs to infer in order to give the right predictions. And so what they observed was that indeed transformers can, as a result of training, perform very well for this, in context learning of things like linear functions as well as e-squares, for example. So as a follow-up to this paper, a paper by Akirek, Schumann, Andreas, Ma, and Zhou in 2023, they went a step further, right? So more than just showing that transformers or language models can do in context learning of simple functions, they explain why they're able to do this. And their explanation was that they implement learning algorithms like ordinary least squares. And they run experiments trying to verify this phenomenon. For example, this plot at the bottom compares the loss of the transformers prediction compared to a number of algorithms, and it very closely matches the loss of ordinary least squares. Sorry, not loss, the output. So the transformers, the predictions by the transformer very closely matches the predictions of ordinary least squares across a lot of different problem instances. They also provide an explanation for how transformers are able to do this. So they came up with a construction that is somewhat complicated. And in order to show that the transformer network has this capability. However, the catch is that because the construction is pretty complicated, it is unlikely that this exact construction is being learned when you train a transformer. So as a follow-up to that paper, there were two works. I'm going to focus on the second one by Oswald and collaborators. So here they gave an even more detailed mechanism for how transformers do in context learning. So earlier we said transformers do OLS, and here they say they do OLS, and the exact way they achieve OLS is by implementing gradient descent in this forecast. And they gave a very, well, not very, but relatively simple construction of the exact parameters you need in order to implement gradient descent, which in turn implements OLS, which in turn does in context learning. And it's sufficiently simple that there is hope that that's what the transformer actually learns in practice. And indeed, they showed some experimental evidence that the kind of parameters they predict do seem to match what the transformer learns after you train it. The catch is that here they focus on an even simpler subset of problems, which is the problem of learning linear functions on a simplified architecture known as the linear transformer. And so that takes us to our first paper, along with a number of other concurrent works, which try to establish theoretical proof for why the transformer ends up learning to implement gradient descent. So in our paper, we show that the parameter configuration that implements gradient descent correspond to certain local or global minima of the transformers. Zhang, Frey, and Bartlett's paper, I think, went a step further in the case of single layer transformers and showed that gradient flow actually converges. When you train a transformer using gradient flow, you will converge to implementing gradient descent, given the right initialization. And we also observe very convincing experimental evidence that this exact set of parameters that's been predicted are indeed being learned. And again, we focus on linear transformers, learning linear functions. So the setting is somewhat restricted. And so finally, that brings me to the second paper I'm going to talk about today, which tries to establish a similar kind of guarantee, but for nonlinear transformers applied to learning nonlinear functions. And the high-level idea here is that we show that each layer of the transformer implements gradient descent in some function space, and the function space is determined by the choice of your nonlinear activation. And there are several restrictions, which I guess I won't mention here, but we'll see as I go into the details later. Okay, so that's the history and motivation of what I'm going to talk about. Okay, so as warm up, let's begin by considering the simple problem of in-context learning of linear functions. So this at the top of the slide is that setup I described earlier, first proposed by Gorg and collaborators. We are given demonstrations in the form of XY pairs, and then I guess on the picture this would be the black points on the demonstrations, and then the query is a red point xm plus 1, 0, and the goal is to predict ym plus 1 given xm plus 1. And I also want to say that this is harder than the standard linear regression because every time you're given an input batch of demonstration, comma query, the theta could change from input to input. So it's not like you can learn a single theta star and be done with it. Right? You really need an algorithm that extracts theta star from the black points. And we'll also begin by considering a simplified transformer architecture called the linear transformer, which removes this softmax nonlinear activation from the attention module. And by stacking these linear attention, we get the linear transformer. So understanding this simple setting will be very important first step towards explaining context learning in more complicated settings later on. And the remarkable thing is that in practice, the linear transformer does very well at learning linear functions. So on the right, I plot the prediction error of the linear transformer against number of transformer layers, and we see that with just a few layers, it achieves very small loss. And this good performance, I think, is really because the linear transformer is very naturally suited for implementing gradient descent specifically on the linear regression objective. Okay, so what does it mean for a transformer to implement gradient descent? On the left, I show a L layer linear transformer, and the input to the transformer is a matrix, of n demonstration XY pairs along with a query. So at each layer I, we can read out a prediction for ym plus 1. And we'll train the transformer by minimizing the objective at the bottom left, which is the error between the last layer's prediction and the true label. And now let's forget entirely about transformers for a moment and ask ourselves the question. So given this problem setup of x, y demonstrations, and we want to predict ym plus 1, how should we do it? And I guess the intuitive answer is the following two-step procedure, right? We look at the demonstration points in black, and we find the best fit linear function, which is the purple line. And once we have the best fit linear function, we'll use that to predict ym plus 1. And concretely, the best fit theta can be found by minimizing the empirical loss summed over the demonstrations. And even more concretely, to find the minimizer of empirical loss, we can run gradient descent. So we run many steps of gradient descent, and eventually we'll converge close to the empirical minimizer. And so what we show in our paper is that there exist stationary points of the training objective such that the transformer's prediction at every layer, which is the blue prediction subscript I, is exactly the same as if you made a prediction using that many steps of gradient descent on theta. So concretely, the prediction after one transform layer is the same as using theta 1 inner product xm plus 1 to predict ym plus 1. The prediction at layer 2 is the same as using theta 2 to predict ym plus 1, and so on for every layer. And furthermore, when the number of layers is 1, we show a much stronger result. Instead of showing stationary point, we can show that the global minimum of the one-layer transformer coincides with one step of gradient descent. And as I briefly mentioned just now, other people have been able to show even stronger results that you're actually guaranteed to converge to those global minimum given the right initialization in the one-layer case. Okay. Now back to the earlier setting. Previously, we assumed that the covariance are drawn from the standard Gaussian, but instead, if the covariance is given by some ill-conditioned matrix sigma, then the transformer instead learns to implement preconditioned gradient descent, where the preconditioner is given by sigma inverse, and this is a bit reminiscent of Newton's method. So in terms of the assumption, we assume that the covariance of the features x and theta are sort of related by this inverse relationship, and that's really a constraint. I guess it's not too unnatural if you think about the setting when you're observing a skewed version of the features which were generated from standard normal distribution. But this constraint is really to make the analysis simple. And in the one-layer case, you can actually have the covariance of x be unrelated to the covariance of theta star and establish, the exact precondition there. And in that case, there's a pretty non-trivial trade-off in terms of how you regularize the different dimensions. But in the interest of time, I won't go into the details.
We don't know the covariance, right? How can it be the same? I think you think that preconditioning is not possible in practice, right? Unless you assume. I mean,
okay, so I see. That there are, I guess, two parts to answering that question. First of all, this covariance sigma is fixed throughout training and test. So there's only one sigma. Then it's believable that that the transformer can learn this sigma over. Yeah, that's true. So ignoring statistical questions of having enough samples, you would learn it. But yeah, for finite training samples, you will learn an estimate of the covariance sigma.
But I guess it still cannot be the same. You never know that it could be approximate. Because any method would have to give an estimate of the covariance or the exact covariance.
So by estimate, do you mean an estimate that's formed using your in-context samples, which is only like, say, 10 of them, or an estimate formed using your entire training set, which is yeah, that's okay. Yeah, all right. So that I agree. So that there's error, statistical error in terms of estimating sigma, which would depend on the number of training samples I have. And we sort of ignored that issue, and we assume we trained on the population. But you're right, that's a non-trivial. An estimator of the precondition for transformer actually. Experimentally, it seems to be that. So instead of that, what else were you thinking might happen?
Right. So I'm just thinking maybe it doesn't really learn this estimator. Instead, learns estimator.
I see. Let me think about that. Actually, this matrix A comes up, is realized exactly in the query times key matrix. So in practice, I guess it's a product of two things, but I guess you can multiply them out after training convergence and compare it to A, and it sort of like tells you what the preconditionary actually learned. And right, and it's probably going to be close to sigma inverse.
I guess what also if you said that it's the same as case step, I'm just saying it cannot be the same. Exact.
Right. Unless I have infinite training samples. Right. So okay, maybe the training objective I should have defined, right? The expectation, if you are a population expectation, then it's exactly then that's believable that it's yeah. Okay. And just to make this idea of implementing an algorithm very clear, here's a short animation for illustration purposes. I came up with this trajectory. So a short animation of the transformer's behavior during training. So first note that there are two algorithms going on here, right? The horizontal axis denotes training steps of the transformer's parameters. And this algorithm can be any of your favorite gradient-based algorithms like SGD-Atom or RKHS. Right? And the vertical axis denotes the algorithm implemented by the forward pass of the transformer. And at any fixed step of training, the transformer can have some fixed set of weights, which can be interpreted as implementing some algorithm. So here I show a 3-layer transformer, and thus the vertical axis involves 3 steps of some algorithm. And so at the start, the transformer has random initialization, and thus the algorithm it implements is essentially a random walk. And then as we train the transformer parameters on the training objective, the parameters begin to converge towards a setup which implements gradient descent. And eventually it learns to implement a 3-step gradient descent. Let me also note that from our theory, we don't guarantee convergence. So this is more like a hopeful illustration. Experimentally, we do observe that. Right. But if it's but we do have a stationary point for validation. Okay. So in addition to interpreting the transformer's action as stationarity, we can in fact show something even stronger. We give precise prediction about what the parameters of each attention layer need to be in order to implement preconditioned gradient descent. And so quick background, each attention module is parameterized by 3 matrices, value, query, and key. We predict that the product of query and key matrices at each layer must equal to sigma inverse. Again, ignoring statistical errors. This prediction agrees very closely with what we observe in experiments. Below, I visualize the query times key matrix of a 3-layer transformer trained to convergence. And we see that in each case, QK almost exactly is equal to sigma inverse. Across multiple experiments with different setups, we always observe the same result. So and it is quite remarkable, right, that this simple prediction of the parameters is consistently being learned each time. So also, finally, I'll make a note about the value matrix, which I didn't talk about. So we do make predictions for what the value matrix will be, and it is something simple. But depending on the kind of constraints we impose, the value matrix will either be close to 0 or close to identity. And this, in fact, lead to 2 different kinds of algorithms. The gradient descent algorithm I've been talking about and will be talking about correspond to the more restrictive setting where we constrain the value matrix to be mostly 0. And in general, when the value matrix is not 0 but identity, the algorithm it implements is a fancier version of, it's much fancier than gradient descent. It's sort of like interleaving steps of gradient descent with steps of preconditioning based on your empirical passion. So it's, but in the interest of time, I won't go into the details of that. And so there's this remarkable connection, right, between the parameters being sigma inverse and the data covariance being sigma. And because of this correlation, the transformer's prediction accuracy doesn't degrade even when the data is ill conditioned. Well, in the sense of due to sigma. Okay, so that sums up our result on linear transformers for learning linear patterns in data. But in practice, the data can contain complicated nonlinear relationships. In addition, the softmax nonlinear activation in the transformer is also very important for it to work well in practice. So in this setting of nonlinear architecture and nonlinear data, can we also say something interesting about what the transformer is doing? On this slide, I illustrate the 2 kinds of nonlinearity we consider. On the left, in blue, we replace the linear function in data by a nonlinear function. And on the right, in orange, we replace the linear transformer by a nonlinear transformer. And we'll reserve the letter H to denote a nonlinear activation in the attention module. so the linear transform we saw just now and corresponds to H equals identity. In practice, H is usually chosen to be softmax. Another popular choice of H is ReLU. And for theoretical purposes, we will also consider the exponential activation, which is very similar to softmax, but without the column-wise normalization to 1. So again, the high-level message is that the nonlinear transformer with nonlinear activation, H, implements gradient descent in a function space. And each different choice of H gives rise to a different function space and thus a different gradient descent algorithm. There are two notable consequences of this perspective. First, this explains how nonlinear transformers can learn nonlinear functions in context. And second, this gives us insights on how to design the optimal attention architecture, which is adapted to your data geometry. And so finally, let me, before stating our results, let me also define a class of nonlinear data that we'll consider. So on the top left, I show the linear data setting, where y is a linear function of x. So this is equivalent to saying that the labels y are jointly distributed according to a Gaussian process generated by the Euclidean inner product. A natural generalization of this is to let y be a linear function of some feature map phi, which is in turn equivalent to saying that the labels y are jointly sampled from a Gaussian process with covariance matrix generated by some kernel k. I will call this a k-Gaussian process, and in fact, we'll consider k's which are symmetric, but not necessarily positive semi-definite, so they are not kernels. And this class is strictly larger than the class of linear functions of feature maps, which are all kernels. So example choices of k include the linear, exponential, RBF, and ReLU. Note again that ReLU is not a kernel because it's not PSD. And so that there's a little class here, not very visible. It is because when we define a Gaussian process, the covariance has to be PSD. So in case of things like ReLU, which are not PSD, we take absolute value on the eigenvalues in generating the sums, which is again not a kernel Gaussian process, but it is a well-defined distribution.
But they may not completely fit together. Maybe it doesn't matter.
Yeah, so theoretically, I guess. Oh, sorry, I missed the last part of your.
Yes, like, not sure if it may not match.
Yeah, I agree. So the function space of what or I guess the right function space to think about when you do finely flipping eigenvalues is not clear. And so some of our theory will apply only when k is an actual kernel. But even when it's not, we can say something about it, which I guess I'll talk about. So to summarize, we'll consider the following setup. Again, we are given the black points, which are demonstrations, and we will train a nonlinear transformer to predict the label for xn+1 in red. And right, so that's the whole objective. And so before stating the theory, let's first take a look at experiments. So here I plot the loss of different kinds of transformer. By different kinds, I mean transformer with different kinds of nonlinear activation against the number of demonstrations you get. So, and I'm going to show plots for different kinds of data. So the first plot on the left, the data is drawn from K linear, which is the Euclidean distribution. So it is the same, it is equivalent to doing linear learning linear function. So on this problem, we see that the linear activated, so linear transformer, so identity activated transformer performs best, much better than the ReLU EXP softmax. In black, I showed the black, the line in black shows the base optimal loss, which is statistically optimal, and the dimension here is I think about 5, which is why you see there is such a sharp drop. At the moment you have 5 samples, you can learn the entire data. Okay, so for, on linear data, linear transformers perform the best. And on the second and third plot, I show the same set of 4 transformers, but trained to learn data generated using the k-ReLU and k exponential functions. So on the second plot, the ReLU activated transformer performs best for data generated with k-ReLU. And for the third plot, the EXP and softmax transformer performs best for data generated by k-EXP. So it appears that the best transformer is the one whose activation matches the nonlinear function which we want to learn. And so is there a way that we can try to explain this theoretically? So to warm up, we'll see that the transformer learns to implement functional gradient descent when the activation H coincides with the kernel. So recall this familiar problem setup. We're given n demonstrations. The query is in red, and the points are generated from some k-Gaussian process. And we'll let the transformer have nonlinear activation H in orange, and we assume that H coincides with the kernel. So this includes the. So that's a good question. So I guess H is applied to this matrix, right? And yes. Yeah, or the it's a so so specifically the actual assumption is that the ijth entry of H applied to this matrix is a kernel of the ith row, is a kernel over the ith row of one thing and the jth column of the other. Yes, there's a door here. Oh, okay. Yeah. So in general, you have like H of something like this is the and so ij is H is entry-wise. Yeah, I think the easiest way would be if H is entry-wise. I'm not sure if it has to be entry-wise. Yeah, I think it's usually so that was something. Yeah, but it's not. But the closely related vision, which doesn't do the conversion, would be symmetric. So that's what I meant by H coincides with the kernel. That includes linear exponential polynomial activations. It excludes ReLU, it excludes softmax. Yes.
So is it like would it be kind of valid to say that if you look at the space of functions being induced by where you are sampling the based on process that you are H is exactly the kernel to that. Think of H, you use H in some linear way to generate
I think so, but I'm not 100% sure I understood your question. Let me come back to you in maybe 2 slides, because I think I'm going to say something related now. So let me double check with you once I've said that to see if that has to do with what you meant. So the assumed H is a kernel, and so what we show is that there are existential requirements where the forward path of the transformer implements functional gradient descent of the empirical least squares laws with respect to the reproducing kernel Hilbert space metric induced by H. So what does this mean? So let's unpack the terms here. So for every kernel H, there exists a metric space of functions. It's called the reproducing kernel Hilbert space. Is generally infinite dimensional, but in the case of linear, for example, you'll be finite dimensional. You can define a loss functional R of f, which is how well any function matches the demonstrations. And the functional gradient H gives the steepest descent direction of R with respect to the RKHS metric. And given this gradient, we can define a gradient descent sequence over the RKHS. So let me get back to your question. Is that sort of what you were?
Yes. Is this sort of like a calculation?
Okay.
And in some way, kernel to the function space of functions that is being induced by the way you are sampling.
Right, exactly. Right. So it has to do with the data distribution. Yes. Why do I need it? Activation function already matched the kernel function. So I guess there are maybe 2 possible questions you could have meant to ask. Are you asking why does it have to be Gaussian specifically, or are you asking why the function k has to show up in the distribution in some sense, in some way? Because I guess the one important point I'm trying to make is that, I have, data generated from some Gaussian process given by a kernel k. And different k's would be different Gaussian process rates, right? Because the covariance matrix would look very different. For example, if you were a linear k versus like an exponential k, right? The covariance would be different, and so the data distribution would look quite different. And the point, one point I'm trying to make is that when you pick a H that matches the K for your data distribution, then you get good accuracy. I could have picked a H, which is a kernel, but it's a different kernel than the kernel that generates my data. Like, if I'm trying to use, say, exponential activated transformer to learn the labels for linear functions, then that wouldn't work nearly as well. Does that answer your question? Okay. All right, so we defined this gradient descent sequence. And so we let fk denote the function obtained by running k steps of this functional gradient descent. And what we can show is that the transformer's prediction at each layer k is exactly the same prediction you get from fk. So it's quite analogous to the linear setting. Yes?
Also, we proved that there is a stationary point, but you have some guarantee that
unfortunately not. Yeah, I'm not aware of any results. I think it should be possible in the 1-layer case. I guess just because for linear transformers, we know in the 1-layer case there's a convergence guarantee, and like a kernel sort of like linear. So that, but in multi-layer, I don't know what would be. Even in the linear setting, I don't know how to show. It does. So exact same kind of convergence to gradient descent we saw in the linear setting. So experimentally, it suggests that maybe one can show something pretty strong. So furthermore, if the nonlinear activation H and the data generating function K, giving your covariance, corresponds to the same kernel, then the transformer's prediction is statistically optimal in the limit of number of layers going to infinity. Statistically optimal in the sense of given this 10 contextual demonstrations, you get the statistically optimal prediction based on it. So when H is a kernel, we have a nice interpretation, but even when H is not a kernel, the transformer still implements a relatively simple algorithm. So consider the same setup as the last slide, only now we do not require H to be a kernel. So we can show, again, that there exist stationary points which coincide to a relatively simple iterative algorithm. So for example, when H is the softmax, this will be sort of taking a weighted average of your neighboring points. So if you're trying to predict X, you'll look at all the other demonstrations, take a weighted average over them, and then of their labels, I guess. And once again, we can make a concrete prediction for what the parameter values at these stationary points are. So here, the stationary point would be realized if query times key is identity. And experimentally, we again verify that the transformer appears to be consistently learning these parameters. So on this slide, I show the plots of QK matrices for a 3-layer transformer. X-axis is training time, so number of steps of atom, and y-axis denotes distance to identity. And each plot shows different choices of data generated from K. But H here is fixed to be softmax. And I will note that similar plots are also observed for other choices of H, like ReLU and linear, but I just didn't show them. Okay, so let's come back to this plot, right? In light of what we showed, it sort of makes sense that the best performance for each kind of data is when the H matches that data. So in the ReLU case, our theory actually doesn't extend there because we have to assume it's a kernel and ReLU is not a kernel. But I guess for some reason it's still the best approximation to the right thing to do. I will also note that if you look here, the orange line is softmax, the red line is EXP, and it's a bit interesting that softmax does slightly better than the EXP activated transformer, even though we predicted that with enough layers, EXP should be statistically optimal. So here's another set of plots. So this is the plot against context line. And so for transformers with more layers, the gap between EXP and softmax becomes very small. And so this is consistent with the theory that as layers go to infinity, HEXP should do as well as anyone else. Another interesting observation is that the performance of softmax becomes significantly worse when less a shorter context line. So the top two plots are when n equals 14. The bottom two are when n equals 6. And we can see that softmax does much better relative to everyone else when n is only 6. So the conjecture is that the softmax transformers for a path ends up implementing an algorithm that is iteration efficient, so efficient in terms of number of layers, but ends up converging to a solution which is not statistically as efficient. Sorry. Okay. So to end, there is one more thing I want to talk about, which is the potential to build more complicated. So in RKHS theory, right, one thing that's very useful is that given two simple kernels, you can compose them following a set of rules and end up getting a much larger class of complicated kernels. So a multi-headed transformer where each head has a different activation. You can do like this a similar thing you can imagine, which is that it effectively lets you to implement things like functional gradient descent or over kernels belong to a big class of kernels obtainable from compositions of H. So for example, here I show a two-headed transformer where one head is the identity activated, the other head is exponential activated. And so here's a set of experiments. I compare three kinds of transformers: linear, one had linear transformer, one had exponential transformer, and two had linear plus exponential transformer. So on the bottom left, when data is linear, you see that the two-head transformer does as well as the linear transformer. In the middle, when data is from EXP, you see that two-head does as well as the EXP transformer, which makes sense, right? You just set the other guy to 0. And furthermore, when I have a K diamond, sorry, I forgot to write the formula for this, but it is basically summing a linear kernel over the first two features and an exponential kernel over the last three features in a 5-dimensional problem. So it's sort of a composing linear with exponential. We can see that the two-headed transformer does better than both linear and EXP. Okay, so to summarize, we saw that transformers can implement gradient descent. In linear transformers, this is Euclidean gradient descent. More generally, for nonlinear transformers with kernel activation, this is functional gradient descent in RKHS. And if you choose the right activation for the problem, we can get a good loss. And we also analyze certain local and global optima for multi-layer and single-layer transformers, and we show that they coincide with the above implementations. So we are all, specifically for this characterization, we can also establish it for nonlinear activations like softmax and ReLU. And we empirically verify that the transformer always seems to learn, implement functional gradient descent, and we verify this on the level of parameters. And two interesting future directions. Well, one is to explore more about how this kernel composition could allow us to learn much more complicated functions. And the other thing is, viewing like deep transformers as implementing a gradient flow ODE, and what is the right metric over the space of ODEs in terms of talking about statistical optimization questions related to training the transformer, which is really training an ODE. So with that, I'll end the talk. Thank you everyone for your attention.
So I guess, so previously when you were sharing this, using different terms of activation, even if you're using the wrong one, it still makes the program. Sort of like
this like this, sorry, like this block, like the, sorry. Like so ReLU is still doing okay on Yahoo.
Sometimes even if the data, so if you pre-train on the data that's irrelevant,
yeah,
you would still sort of.
Yeah, I think so. I guess there may be a way to quantify exactly what price you pay for this mismatch. And also I think it would be a function of the number of demonstrations. For example, like in the case of softmax, right? It performs much better when demonstration, you have a lot of demonstrations. So I think some things are sort of have like this universal property, like RVF kernels. If you have infinite demonstrations, then it can fit any function I want. So maybe I think for reasons like that, might be why some of these are doing decently. But also in other cases like linear, right, it's pretty much slower.
So is there possible to pick data distribution so that when you pre-train all those irrelevant data, it actually hurts data performance?
That's a great question. I think so. I think you can design some pretty degenerate kernels. I'm not 100% sure that you can make the line go up, but I guess you can. I'm not sure.
Is this possible visualization for data set?
Good question. Let me think. I think just by virtue of the way things are set up, it's always initialized at 0. Like you initialize at the 0 function. So going from layer to layer. So the 0th layer always outputs 0, which is the 0th. Abhishek, did you have a question? Okay, sorry, I thought you raised your hand.
I have a question.
Yes.
What is special about the gradient descent or functional gradient descent algorithms that the transformers implicitly learn those instead of some other algorithm?
I'm sorry, would you mind repeating the question? I missed the first half of what you said.
Oh, sorry. What is special about the gradient descent or the functional gradient descent algorithms that transformers somehow implicitly learn those algorithms instead of some different algorithm? I guess it may be related to the underlying data set, but I'm not sure about it.
Yeah, that's a great question. First thing I will say is that when I impose no constraints on any of the parameter matrices, transformer actually implement this fancier thing than gradient descent, where you take a gradient step and then you precondition your data, and then you take a gradient step and precondition your data. So I guess in that sense, gradient descent really is not special in the sense that it's the optimal algorithm we can possibly implement given entire freedom over the key value matrices. At the very least, the transformer will also learn like this preconditioning step. But under the constraint that the value matrix is largely 0, it does end up learning gradient descent or functional gradient descent. I want to say, gradient descent is nice in the sense that it's locally, steepest descent, but I don't know why that makes it the best algorithm to end up implementing. Sorry. Also, one more thing I want to add is that I guess the distributions of data I talked about in terms of covariances has been pretty nice so far in this entire talk. But in the case when, for example, linear regression task, where your theta has identity covariance and your features have some non-trivial sigma, the transformer actually doesn't, in one layer at least, it doesn't implement one step of gradient descent, right? It implements one step of some preconditioned thing with the non-trivial statistical trade-off over each coordinate. So I guess whether you can call that gradient descent is, yeah, maybe that's still preconditioned gradient descent.
Okay, I see. Thank you.
Yeah, it doesn't. Maybe it has also to do with the way attention is just constructed, because you can. I mean, attention. My gut feeling is that attention does have affinity for gradient type algorithms. It just cause setting the key query matrix to identity makes it already in the gradient sense. I feel like if you had, I don't know, some parameter matrix that keep track of momentum or something, then maybe you'll more naturally implement like this acceleration. Yes, sorry.
We go to the slide where you are for the fixed point for the we have a kind of yeah. So then it is like delta is evaluation functional or
This one?
yeah.
Oh, what's the evolution of? It's a scalar step size.
So I mean, how are you exactly fitting?
So delta?
No, overall.
How am I varying this? Is it some kind of optimal solution? I don't know. I don't know what f will converge to in the limit of infinite layers, if that's your question. if you were a kernel, I would know it's the base predictor involving the kernel matrix, and there is a relatively simple version. But when it's something like Revit, for example.
If it looks like you have written it down as linear combination of combination cross as a kernel evaluated at xi.
Yeah.
So, I mean, this is like one way to, I mean, in one sense, it looks like a representative.
Yeah, sort of. It does. So when H is a kernel, I think it's exactly like you said. It looks like a representative. Absolutely. Yeah, exactly. Exactly. You're right. So if H is a kernel, I think